Alrighty, we are here for intermolecular forces today. We're in the states of matter, solids, and liquids unit. So we're going to cover IMFs, we're going to cover solids, liquids, their properties, vapor pressure, all sorts of good things. It's a very conceptual unit. There's a lot going on here, not really any math, which is good. But there's a lot that we really have to make sure we understand and understand well and know how to explain. So when we're thinking about how we're writing for our FRQs, think about the CER method, claim, evidence, and reasoning. You need to make sure you're answering the question, making sure you're providing evidence, whether that's data from a table or something of that regard, especially like boiling point data. Those are things that we'll look at a lot. And your reasoning is the deep conceptual understanding of what's going on with the electrons and why we're seeing these kind of interactions. Okay, so first off, intramolecular forces. We just spent a whole lot of time in the bonding unit talking about intramolecular forces. Those are the bonds that hold our molecule together. But now we're looking at intermolecular forces, which are the forces between molecules that hold the molecules together. So the diagram here, we tend to use this kind of dot system or dashes to show intermolecular forces, whereas with bonds, we're looking more at lines. So these are the things that hold solids and liquids together. When we're getting into the gas phase, we just finished talking about gases. When we're in the gas phase, there is the assumption that there's minimal interaction between my molecules, and that's what makes them ideal. When there is interaction and there are intermolecular forces forming, that's when we tend to view them as real gases. So there's a slight connection there. In the solid and liquid state, the intermolecular forces hold us together, and they're much weaker than ionic or covalent bonds. So, for example, I've got HCl here. The energy needed to vaporize it, which would end up breaking the bonds, the energy needed to vaporize it is 16 kilojoules per mole. So that's just turning it from the liquid to the gas phase. That's breaking the intermolecular forces. But then the energy to break the bond itself, if I was to break it into its ions, is 431 kilojoules per mole. So quite a substantial difference there. So when a substance melts or boils, we know that the IMFs are being broken, not the bonds. So that takes me to boiling point. Like I said, we're going to look at some boiling point data, melting point data, a lot of different physical properties, and all of these things are a reflection of intermolecular force strength. A high boiling point indicates strong attractive forces, and a high melting point also reflects strong attractive forces. So higher temperatures, therefore more kinetic energy. More kinetic energy causes more vibrations, which then causes the intermolecular forces to dissipate because we have more movement going on. The four main kinds that we're going to look at are ion dipole forces, dipole forces, London dispersion forces, and hydrogen bonding, which is a special type of dipole force. These are all things that are covered in first-year chemistry, but we're going to also talk about a few special scenarios, but these are the four main ones to know. So ion dipole forces, it's the interaction between an ion, something that's positively or negatively charged, and a dipole. The key here is that whatever the dipole is in the molecule, that partial negative or partial positive will form an attraction with the opposite charge ion. So notice in our water molecule here, the water molecule has oxygens which are slightly negative, and those slightly negative oxygens, the slightly negative oxygens all form an attraction for a positive ion, and all the positive hydrogens form an attraction for the negative ion. So the orientation of water matters here because that's where the intermolecular forces are forming. Ion dipole is the strongest of the attraction types we're going to look at. Hence why we relate it back to first year chemistry and colligative properties. We're talking about boiling point elevation or freezing point depression. When we add more particles to our solution, we increase the number of ions, which increases the number of ion dipole forces, which is why the boiling point gets even higher when we're looking at solutions with solutes dissolved in them. And it's also why we use salt to salt the roads in the winter, because the number of particles help drop the freezing point, which allows water to freeze at a cooler temperature, effectively allowing the roads to remain unfrozen at the normal freezing point, which is 32 degrees Fahrenheit or 0 degrees Celsius. Dipole forces, this is typically found in polar molecules, two molecules of the same substance, or it could be a different substance. As long as it has a permanent dipole, forms a sense of attraction with each other. Typically, you have highly electronegative elements. The greater the electronegativity difference across a bond, the stronger the dipole. So an increased dipole strength results in stronger dipole forces. So again, these exist between neutral polar molecules. It is weaker than ion dipole forces. If two molecules have about the same mass and size, then the dipole forces will increase as the separation of charge increases. So again, that's increased polarity, which means more separation of charge, which means a stronger dipole. You see where I'm going with this. Every little thing has an impact on the other. It requires quite a bit of attention to detail, and that's what this unit's all about. So one thing keeps on leading to another. So again, here's some nice data looking at a couple of different covalent compounds. Propane is nonpolar and has roughly the same mass as acetaldehyde. But the thing is, acetaldehyde has oxygen in it, which makes it a highly electronegative group, that oxygen group, which means there's going to be some dipole there. And if we just compare the dipole moments, even though they're roughly the same size, this one has a 2.7 Debye dipole. Debye is the unit that we use to measure dipoles. You don't really necessarily need to know that, but if you see that annotation or that word, that's what they're referring to. You see that acetaldehyde has such a great dipole moment in comparison, even though the sizes are the same. And so as a result, we get a much higher boiling point because the intermolecular forces, the dipole forces in acetaldehyde are much stronger. All right, concept checked. Do you expect molecules with dipole interactions to have a low melting point and low boiling point, low melting point and high boiling point, a high melting point and low boiling point, or a high melting point and a high boiling point? Hopefully, shows D. Stronger dipole attractions are going to have high melting points and high boiling points. That brings me into hydrogen bonding. This is a unique kind of dipole force. It is actually stronger than dipole forces. So to recap, we should probably rank them. So far we've got ion dipole, and then we've got hydrogen bonding. Apologize for the noise, the dog's scratching at the window to come in. Hydrogen bonding, and then after hydrogen bonding, we just got regular dipole. All right. So hydrogen here is attracted to the nitrogen, oxygen, or fluorine of a neighboring molecule. The reason why is those things are highly electronegative, and so this forms a greater attraction than just a typical dipole. Because those are electronegative, they pull the hydrogen in closer, so the bond length between those highly electronegative groups and the hydrogen is rather small, and so then it allows there to be a pretty significant partial positive charge there. This also is seen in water. It's why it typically has a high boiling point. Here's some other examples. Here's NH3, has some hydrogen bonding occurring in it there in the middle picture here. And we also have NH3 forming hydrogen bonds with water. When we look at the graph on the left here, you see that the boiling point just goes up, up, and up with each group. And again, it relates to electronegativity. So group 4, those are things like carbon and silicon. Those aren't very electronegative, and in fact, most of those things are viewed as nonpolar. Whereas as we go across from left to right on the periodic table, we get more electronegative. If we get more electronegative, we also increase in polarity, and then we tend to see these spikes in the boiling point from there. Now, if you're also looking at HF, H2O, and NH3, they are much higher than the rest of their neighbors here. And again, that's because these particular ones experience hydrogen bonding, which is much stronger than a typical dipole force, which you might see in HCl or H2S. This one you're probably not going to see as much, but it's good to just know about. When a dipole approaches another nonpolar molecule, so a polar approaching a nonpolar molecule, the partial charge on the dipole can either attract or repel the electrons of the nonpolar particle. You know that nonpolar molecules have a relatively even separation of charge. And the larger the molecule is, the more electrons there are. So increased amount of electrons means a larger electron cloud, which then can increase what we're going to call the polarizability of our molecule. So as water approaches, water is very polar and has hydrogen bonding, and its large dipole will cause a nonpolar oxygen molecule to be rather distorted as you look from the left picture to the right picture. This is because of the repulsion that's occurring between the negative of the oxygen in water and then just the normal oxygens in O2. We call this an induced dipole because we're inducing. Inducing just means to cause to happen. So we're causing a dipole to happen in our nonpolar molecule by putting a polar molecule next to it. Think about what happens when you put a couple of magnets into each other. If they're facing the right direction, they're going to form an attraction. If they're facing opposite directions, you're going to feel that force pushing apart each other. This leads into our discussion of induced dipole forces, otherwise known as London dispersion forces or even van der Waals interactions. All three of those names refer to the same thing. Van der Waal, I should write that down. So van der Waals interactions. Just in case the AP exam refers to any of those things in that manner. This is the weakest intermolecular force, but it exists between all molecules. It's a temporary instantaneous dipole that may be created by the uneven distribution of electrons around your nucleus of the atom. Like I said, if we're thinking about the electron cloud getting close to an electron cloud of another, there's some repulsion there, but there's also still some attraction between the nuclei of one molecule and then the electron cloud of another. So they kind of stick together, but they also distort each other at the same time. So that's why we call it induced dipole, or London dispersion. If you use the abbreviation LDF, the AP graders and readers will know what you're referring to. LDF is London dispersion. You can call them van der Waals forces. LDF saves a lot of time just because it's a nice abbreviation. Like I said, they rise to the Coulombic attraction of the temporary dipole with the electron distribution of in the neighboring atoms and molecules. So one temporary dipole can create another one, and then it's an endless domino effect. This is why things that are nonpolar still tend to stick together. If you think about oil, oil can exist as a liquid because those are nonpolar molecules, and they have a large amount of dispersion forces with each other. The larger the molecule, the greater the number of electrons, like I said before, and we get something that's more polarizable. That is the official recognized language that the AP graders are going to look for. If something is more polarizable or has a greater polarizability, then it can have a stronger London dispersion force. So London dispersion forces increase in strength as the molecular weight increases. And so what I'm going to say is be careful not to use mass as a justification here, because the mass, while it does have a correlation, it's only important to tell us the information that, hey, higher mass means higher electrons. Therefore, if we have a greater number of electrons, we have a larger cloud, and then a larger cloud means we are more polarizable. That's our justification. If we're more polarizable, we can have a stronger London dispersion force. There are times where, even though London dispersion is considered to be the weakest of the intermolecular forces, if it's large enough, it could actually have a greater effect on the boiling point than some of the other intermolecular forces. So if you look at some of this data here, that's where things are interesting. Fluorine and chlorine tend to be gases at room temperature, but then if we look at bromine and iodine, they're much larger, almost double and triple the size of fluorine and chlorine. And so as a result, they have much higher boiling points. So this explains why some of them are liquid at room temperature. When we're looking at noble gases, as they increase in size, they get larger and larger with their electron clouds, and so their boiling points get higher as a result. I remember it was either last year or a few years ago, there was an FRQ problem where they asked you to use your knowledge of intermolecular forces to justify why one boiling point was higher than another, but it wasn't what you would have expected. And so the answer ended up being, well, the London dispersion forces in this particular molecule are much greater because it's larger, even though it's nonpolar. And so your justification would have had to been, well, the boiling point for this one's higher because this one, even though it's nonpolar, is larger and therefore more polarizable, whereas the other one was smaller, and even though it had some strong dipole-dipole forces, it's not quite enough to have a high enough boiling point to be comparable to the nonpolar substance. So sometimes they might make you explain things that are out of the ordinary, and that's something to be on the lookout for. London dispersion forces can also depend on the shape of our molecule. So the greater the surface area that's available for contact, the greater the dispersion forces. So we have pentane and neopentane. The one on the right has less surface area. These are isomers of each other, and so there's less force involved. So it just says spherical nonpolar molecules tend to have lower dispersion forces than long straight chain molecules. If we actually think about this in the context of lipids, which I'll talk about in a minute, we know that lipids, your fats, have those hydrophilic polar heads, and they have the hydrophobic long nonpolar tails. And those nonpolar tails, because they're relatively straight, they tend to stick together more, and that's why fat tends to build up over time, depending on the kind of fat, which is pretty cool. This one you probably won't see as much. This is an ion-induced dipole. So if an ion gets near a nonpolar molecule, it'll cause some slight distortion, but it's relatively minor in the grand scheme of things. So again, just to recap, London dispersion forces are a function of the number of electrons in a given molecule and how tightly those electrons are held. So as the strength of the London dispersion force increases, that means the number of electrons must have increased as well, and therefore we are more polarizable. This might be a good time to just pause and digest this lovely flowchart here that really recaps everything we just discussed. Otherwise, I'm moving on. So here's a quick little summarizer. I've got 4 different types here. Go ahead and identify the IMFs in each one. So Br2 and CO2. calcium chloride and H2O. Okay, NH3 and H2O. And finally, HBr and HBr. All right, let's see how we did. All right, so the first two are non-polar substances. Even though CO2 has dipoles, those dipoles do cancel each other out, so we're really only experiencing dispersion forces here. Calcium chloride's ionic, and water, oh, I'm sorry, I missed one here. Oh no, I didn't. Water has hydrogen bonding and dipole-dipole forces, but we're specifically looking at the ion dipole force occurring between water and calcium chloride, but there is still some dispersion here. NH3 and H2O. NH3 can have hydrogen bonding, and so can water, so this mixture definitely is going to have a high boiling point as a result. It has all three. And HBr has dipole-dipole forces and dispersion forces. Here's another nice little graphic just looking at some diagrams of each of the different forces in action. Might want to pause and just digest what's happening here. Some of the things that matter when it comes to intermolecular forces are the physical properties, and I think this is where I'll wrap up shortly. Just want to talk about why we care about IMFs in addition to boiling point and melting point. It also impacts our like dissolves like rule with solutions. So a reminder that polar substances can dissolve polar substances or ionic substances because they've got the dipoles with the separation of charge, whereas nonpolar things can only dissolve in nonpolar substances. So there's a great picture here of hexane, which is nonpolar, tends to be a straight chain carbon with 6 carbons. And you'll see that even over here, if you shake it up, this one particle in particular mixes in with the water, but it doesn't form any attractions really, and so you'll start to see these little bubbles. If you've ever shaken up oil and water before, which you probably have if you've ever had salad dressing, you see emulsions, which are bubbles in pockets of oil that are trapped in between water molecules. So again, coming back to that lipids conversation, and then I think I'll call it a day here. Lipids and fats, they have polar heads and nonpolar tails, and therefore, oh, I spelled soluble wrong. Therefore, they're partially soluble. And I got a great picture here. It's really cool. It actually shows all the water interacting with those polar heads of your fatty acid chains or your lipids. And what's also cool is that the reason lipids stick together, if you're looking at like a lipid bilayer, you end up getting hydrogen bonding between each of these because of the polar groups that are happening. So they all tend to stick together in these rows because of those hydrogen bonds with the polar heads occurring both with each other and with water, which is pretty cool. And then these nonpolar tails also tend to stick together, like we said, because they've got these nice, long, relatively straight chains, and they have greater surface area, so that's even another reason for them to stick together, because they've got large London dispersion forces because they're very polarizable. Here's just another example, methanol, which is CH3OH. OH is polar and experiences hydrogen bonding, but the CH3 group is nonpolar. So if you really focus in on that methane group there, or methyl group, the CH3, they tend to be excluded from the interactions with water because they're hydrophobic. And that is all for today.